Thanks for coming, everyone. So I'll be talking about my PhD results. So I submitted my PhD in April this year, and I still need to do corrections, so I'm not quite a doctor yet. That's all good. So I'm just talking about in situ uranium-lead dating or geochronology of hydrothermal xenotime and monazites to date gold mineralization in the Northern Capricorn Orogen. Okay, so the Capricorn is located between the Pilbara and Yilgarn Cratons, and it's a zone of deformation, metamorphism, magmatism, and basin formation, which marks the two-stage assembly of the West Australian Craton by 1950 MA, and then it also records 5 subsequent episodes of intracratonic reworking. So in 2010, Geoscience Australia, Auscope, and the Geological Survey of Western Australia all collaborated to acquire this seismic transect, which is here, to image the crustal architecture of the Orogen, including the cratonic boundaries. It was completed over 3 segments, and I'll be talking about the northernmost part, which is just up here, and looking at some of the gold deposits which are associated with the faults in the area. So the seismic transect identified 5 major faults, and of particular importance are the Nanjilgardi here and Bearing Downs. And these have close spatial relationship with the gold occurrences and also some of the base metal deposits in the area. So prior to this study, there wasn't really much known about the timing of the gold mineralization, and it was all thought to be associated with the Capricorn orogeny, which back in around 2010 was thought to be a collisional orogeny, whereas now we know that the amalgamation of Western Australia was a 2-phase process, and the Capricorn orogeny is actually an intracratonic reworking event. So otherwise, the gold was also thought it could be associated with this previously dated Mount Olympus deposit, which was dated at 1738 MA by xenotime, and I'll be talking about this a bit later in the talk. Okay. So since the seismics got done and we realised that the geological history of the area was a bit different than first thought, that was what drove this PhD to become a project. And so the project aims were to look at the timing of gold mineralisation and also date the host rocks which host the ore deposits, and also to try to link the timing of gold mineralisation to the tectonothermal evolution of and crustal architecture of the Capricorn, and then also to identify any structural events which are associated with gold mineralisation, and then look at how we can use all this information to improve our exploration targets. So phosphate minerals were the main geochronometer that we used. However, we did also look at badleites and zircons, and I'll talk a bit about those as well. So in situ, phosphates are important because they're rare earth rich phosphate minerals which are high in uranium and thorium, and they are good for dating rocks. So in hydrothermal ores, they're quite common. They usually form small crystals, and when these are intergrown with ore stage alteration or sulfides, such as up here, we can link the timing of the phosphate growth to the ore formation and date the mineralisation that way. So they're useful because they're resistant to isotopic resetting over a range of temperatures and pressures, and we don't get diffusive lead loss at temperatures less than about 700 degrees, which for gold deposits is usually what we're sitting in. Whereas at these low temperatures, we get dissolution and reprecipitation, and we get preservation of core zones and also overgrowths of younger rims. So we can date more than one vent with the individual crystals. So in situ geochronology is a bit different to traditional methods where we crush and separate the minerals we want to date, such as zircons, and put them into a mount and date individual crystals. So for in situ geochronology, we collect the samples in the field in geological context, so like making notes of any deformation and also doing geological mapping. And then when we get back, we make these polished thin sections and then do petrography, so optical and scanning electron microscope, and have a look to see if we can find any minerals that are amenable to dating, and also whether they're large enough, so we can date things that are about 10 microns in size. And also look for zones, so cores and rims, such there, so we can date multiple events in the individual crystals. And so once that's done, we get a drill and drill out the little holes with the crystals in them and put them in a shrimp mount, like there, and then re-image them so we can find them when we're doing our analysis. And all the analysis was done on the shrimp at the John DeLader Centre at Curtin University. And then data was reduced using squid and isoplot to plot the data. And once we got our ages from that, we were then able to link it back to what we're seeing in the field. And this is really useful because you might have more than one event in the one rock, and if you've crushed and separated it, you're not going to know what it's related to. And also, by doing it this way, we can date much smaller things that wouldn't survive that crushing process. So if we have crystals that are 10 microns in size, we can actually date them where you wouldn't ever be able to pick something that's that small if it actually survived getting crushed. So the first prospect we looked at was the Paulsens gold deposit, which is situated in the Wailu inlier on the southern Pilbara margin up here. And it's associated with the Nanjilgardi fault, which is one of these major faults which we can see extending down to the mantle in the seismic transect. So Paulsens is an orogenic gold deposit, and it's formed where we get this Paulsens mine gabbro, which is a gabbroic dike which intrudes into the sediments of the Fortescue group. And during regional scale deformation, we get reactivation along the Hardy Fault, which is the second order structure of the Nanjilgardi, and we get brittle failure of the gabbro and formation of this 40-metre wide quartz sulfide vein, which has mineralisation sitting on the upper and lower margins of the vein walls, so here and here, and it's known as upper zone and lower zone, which are the two main ore bodies. So upper zone mineralisation is these massive sulfide veins shown up here, and we don't really see a lot of visible gold in hand specimen in these, and whereas at lower zone it's a bit different, so we get these laminated quartz carbonate veins, we get not so much sulfides in them, we get a lot of wall rock inclusions and graphitic stylolites forming, and we get a lot of visible gold associated with these sort of carbonaceous stylolites and wall rock inclusions in there. So different styles of gold that we see at Paulsens, so the primary gold forms in the sulfides, so we get these little rounded gold inclusions as well as chalcopyrite up here, and that's interpreted to have formed during the pyrite crystallization. And then when these pyrite veins undergo later deformation, we get remobilisation of the gold, so we get local remobilisation shown here, and we also get remobilisation of gold along with chalcopyrite and pyrrhotite along the fractures where the pyrites become brecciated. And then another type of gold that we see is from another prospect nearby, the Gabbro Offset prospect, which is located a couple of 100 metres to the west of the main Paulsens ore body. And we tend to get these quartz carbonate veins and get these really, really high-grade golds associated with the margin of the veins there. So first off, we wanted to date the mine gabbro, and this was done by in situ badleite dating. And the badleites are shown here, so they're euhedral, and we get zircon fringes around them. So they provided a crystallisation age for the gabbro of 2701 MA. And then second, we wanted to look at the timing of the gold mineralisation, and so we did this with xenotime. We have two textural settings for the xenotime crystals that we see. So first off, we see these euhedral xenotimes which are interlocking with the pyrite, which has gold in it. So this sample has about 21 parts per million of gold, and it was one of the samples we saw the rounded gold inclusions in there. And then when the pyrite has been brecciated during the later events, we get this dissolution and reprecipitation where we get these younger rims around the older cores. So we dated the euhedral xenotimes in the core zones, and that gave us an age of 2403 MA, which is associated with the timing of fault reactivation along the Hardy Fault. So additionally, at this time, we looked at some gold prospect called Paulsens East, which is just to the east of Paulsens, a couple of 100 metres. And here we get these narrow sort of quartz carbonate veins. And this one here has a grab sample assay result of 6.65 grams per tonne of gold. So we know it's mineralised. And in the alterations surrounding it from up in here, we have the host rocks are pervasively altered to pretty much all muscovite with a little bit of quartz and carbonate. And we get these really large monazite crystals in there, which are intergrown with the muscovite, which indicates that they formed at the same time. And these also gave us an age of 2403 MA, which we're interpreting to represent the timing of hydrothermal fluids moving along the faults and gold mineralisation. So we see a second hydrothermal event at 1730 MA. And this is not associated with gold mineralisation, But we get, along the Hardy Fault, we get this high straight zones. We start to see these porphyroblasts here, which are possibly former Andalusites, and they've been totally replaced by monazite and florencite. And the monazite in these yields an age of 1730 MA, which we're interpreting just to be hydrothermal fluids during fault reactivation at that time. So next we wanted to look at these dissolution reprecipitation rims on the xenotime in the brecciated pyrites. And we've linked this to the timing of this gold chalcopyrite and pyrrhotite, which has been remobilised along the cracks and fractures. So as the pyrite's been deformed, any of those euhedral xenotimes start to dissolve and recrystallise, and then we're getting remobilisation of gold at the same time. And this is happening at 1680 MA. So we also see this age at the Gabbro offset prospect. We have this little vein here, which has a gold assay of 41 parts per million. So it's got quite high gold in it. And as we know, the gold mineralisation in this area tends to form as these sort of free gold along the quartz vein, which that sample's not from there, but yep. So in this sample, we have xenotime, which has intergrown with the calcite crystals, and that's come back with an age of 1655, which we're interpreting to be that vein emplacement and also associated with the gold introduction. And also you can see that there's this one single spot of 2400, and that's likely to be coming from the alteration surrounding it, which we also dated, and that was 2400 MA, so it's likely that it's preserving some of that previous xenotime in the host rock. Okay, so the second prospect we looked at was the Belvedere deposit, and this is located 6.5 kilometres to the southeast of Paulsens. So Paulsens is that one, Belvedere's the little one, and it's also situated along the Hardy Fault, which is associated with that Nanjil-Gardi Fault. So it's similar to Paulsens, as in it's sitting in a mafic dolerite this time. And so you can see this here is the Paulsens dolerite. So it's generally north trending, however locally it just intrudes along this Belvedere fault and changes orientation to a northeast strike. And where it changes orientation, we start to get mineralised quartz sulfide veins, so shown in here. So the reason I wanted to look at this prospect was previously everyone had thought it was the same age as Paulsens, however, and associated with the Capricorn orogeny. However, the Paulsens age was much older than we expected, and also we had 2 gold events. So I started having to think about the different veins or dikes in the area, and it's pretty obvious we get all of these sort of north trending and also another suite of dikes in similar orientation, cross-cutting the gold mineralisation. So just from the cross-cutting relationships, it's not the same age as the Paulsens ore body. So it's pretty clear that it's cross-cutting it. So the gold mineralisation at Paulsens is similar, or Belvedere is similar to Paulsens. However, it's associated with arsenopyrite rather than pyrite, and we get late-stage galena opposed to the chalcopyrite and pyrrhotite. So in the arsenopyrite, which is this sort of medium grey, we get these large gold and gold inclusions in there. So that's directly linking the gold mineralisation to the sulfide formation. And so we dated the host rock, so the Belvedere dolerite with in situ badleites again, and these gave us an age of 82, which again significantly younger than the Paulsens mineralisation. So gold mineralisation we dated with xenotime, and we have ore stage alteration like muscovite intergrown with the xenotime, and we also have xenotime which is fully encased in the arsenopyrite as shown here. And so these indicate that the timing of xenotime and mineralisation was synchronous, and it's given us an age of 1680, which is the same as the timing of gold mineralisation at Paulsens, the second event, and we're associating this with fault reactivation, which is likely to have occurred during the Mangaroon orogeny, which is 1680 to 1620 MA. So additionally, at Belvedere, a few hundred metres away from the ore body, we have this muscovite schist, and in this we have these xenotime crystals which are aligned along the S1 fabric, and also we get them aligned in these quartz porphyroblasts in there. And these yielded 2 different ages, so 2260 and 2360 MA. And we can't really differentiate them between textural settings, but one of them's definitely associated with the fabric. And so the 2260 age is within uncertainty of the youngest age of the ophthalmian orogeny, and I'll come back to these samples later on in the talk. So the third prospect we looked at was the Mount Olympus gold deposit, and this is located 150 kilometres along strike of Paulsens and Belvedere, so just down in here, also along the Nanjalgarh Fault. So this is a little bit different again to the other two prospects. So it's associated with the Zoe Fault, which is a second order structure to the Nanjalgarh. And we see the Zoe Fault here. It separates the coarse-grained siliciclastic rocks of the Mount McGrath Formation from more dolomitic rocks and mudstones of the woolly dolomite. And we see two different types of gold mineralisation. So we see fault-hosted gold mineralisation here, and also this strata-bound gold mineralisation, which is in the coarser units in the woolly dolomite. So again, I wanted to have a look at this prospect. It has been previously dated, but I wasn't quite sure if I agreed with the previous date. So previously it was dated at 1740 MA, which the researchers linked this to an Australia-wide collision, linking the timing of this deposit with Pine Creek orogeny and also the Tanami gold deposit. However, we now know, after further work's been completed in the area, that there's no orogenic events around this age in Northern Australia at all. So that, and also on top of that, it was previously interpreted as an orogenic gold deposit, but it has a lot more characteristics of a Carlin type deposit, which I'll talk about soon. And also the main reason was this is their data plotted as a probability plot, and it has three age modes in it. So one's at 1770, which is the Capricorn orogeny, the 1820 to 1770 Capricorn orogeny. Then this 1730 age, which they have as gold mineralisation. And also then we have one at 1695 MA, which is not the best age, but that's within uncertainty of the Mangaroon orogeny. So gold mineralisation, as I said before, is strata-bound ore and also sitting along the fault. The alterations associated with removal of carbonate and addition of cerussite and quartz, which is similar to what you're seeing in the Carlin type deposits. It also did pyrite trace element mapping, and these have the same ore signatures as what there is at Carlin with gold, arsenic, copper, antimony, mercury and tellurium. And additionally, the gold forms as a solid solution in arsenium pyrite, so that's these square bits around here, whereas orogenic gold tends to be associated with veins and visible gold and lots of sulfides and addition of carbonate. So, okay. So from this sample, we sampled three different rocks, and we have one from the Zoe Fault and two from the strata-bound ores. And these gave us three ages. We actually got the same results as previous researchers, which was good, because then we could associate them with what textures we thought were associated with gold. So unlike the previous work, we actually think that the 1770 events linked to the gold mineralisation opposed to the 1730, and several reasons for this. So firstly, we have one sample, this one, which is from strata-bound ore, and it only has an age of 1770 MA. We also know that this sample's mineralised. It has a gold assay of 2.67 parts per million of gold, and also it's the only sample where we had a clear textural relationship between the xenotime and ore stage arsenium pyrite, shown here. So for those reasons, we're linking that to the timing of gold mineralisation, opposed to this 1730 event. So finally, we looked at the Star of the West gold deposit, and this one's located in the middle of the Ashburton Basin and is situated along the Bearing Downs Fault here. So this is much smaller than the other prospects we've looked at, and mineralisations, the quartz vein that comes through here, but the gold's sitting in the alteration zone surrounding the quartz vein. There's no production figures for here, but average gold grades are supposed to be around 5 to 6 grams per tonne. So it's just a close-up of the alteration zone. We get pretty much pervasive muscovite alteration. You can't really see it here, but there are these little cubic pyrites, which are up to about 2 centimetres in size. And what we find is, looking on the scanning electron microscope, is in these oxidised pyrite, we get these tiny little gold inclusions. And we also get gold throughout the matrix of the alteration zone, which is pretty small. You can't really see it on any of the images that clearly. So in this sample, this is monazite in here, which, I'll talk about in a sec, sorry, wrong slide. Okay, so we did have xenotime and monazite in the matrix of the sample, and these ages are a bit older than what we saw for the mineralisation, so they're 1815 and 1830 MA. We're interpreting this to be detrital monazite and xenotime. It's consistent with the existing zircon dates for the sediments for the Ashburton Formation, and also this rounded one has indication it's been transported during sedimentary deposition. Yeah. So timing of gold mineralisation. So we tried to date the monazites that were intergrown with the pyrite, but these had really high common lead in them and no uranium, so we didn't get anything meaningful out of them. But we did get xenotime, shown here. It's got these little muscovite inclusions in them. So we dated the gold mineralisation using the xenotime, so because they're intergrown with the Ausstage alteration minerals, we're assuming that that's associated with the hydrothermal fluids and fault reactivation at that time. And so that was at 1670, which is within uncertainty of all the ages at the other gold deposits, and also the timing of the Mangaroon orogeny. So finally, we looked at the Amazon shear zone. So this area is in the Wailu Inlier, so up in here. It's about 6 kilometres away from Paulsens, and it doesn't have any gold mineralisation. However, it's one area where we can clearly link the timing of fault reactivation to hydrothermal fluids, which up until this point we'd just been interpreting based off the proximity of the gold deposits to the faults and like geological interpretations. So at Amazon shear zone, we see evidence of pre-deformational veins. This one's a syn deformation, and then these two cross-cut the fabrics, so they occurred after deformation. So in this one here, B, we have evidence that the deformation was occurring as the veins were being placed with these curved twin planes. And we also get these really large euhedral xenotime crystals intergrown with the calcite, indicating that they crystallised at the same time. And these were dated at 1675 MA, which is pretty much dating the fault reactivation during the 1620 to 1680 MA Mangaroon orogeny. So from this PhD, we showed that the tectonic evolution in regards to gold mineralisation is significantly more complicated and different to what was previously interpreted. So prior to this, everything was thought to be associated with the Capricorn orogeny, which is, here, at 1770 to 1820 MA. And although we do have gold mineralisation, it's not the main event. So we also have two later hydrothermal events at 2200 and 1730. So one thing we noticed was all the gold is associated with orogenies. So the Mangaroon orogeny, we get a lot of widespread gold mineralisation through the area. And then the Capricorn, we have that Carlin type gold mineralisation at Mount Olympus. And then at 2400 MA, we have gold mineralisation at Paulsens. And so at 2400, we're thinking that this might actually mark the beginning stages of the ophthalmian orogeny, which was previously thought to occur from 2200-ish to 2145 MA. And there are several reasons we think that the ophthalmian orogeny is longer lived than what we previously recognised. So firstly, we have orogenic gold mineralisation. And then additionally to that, we have evidence of widespread hydrothermal activity throughout the whole Pilbara region and also the Northern Capricorn. So there's resetting of high uranium zircons in the Hammersley group, interfacious mudstones at 2400. And then we get this younging to the south monazite growth, which is within uncertainty of those from Paulsens and Belvedere throughout the Western Pilbara, which are the ones in the red boxes. And also there's evidence in the stratigraphic record that something significant's happening at this time. So the Churi Creek group has a whole heap of unconformities all through it. Also, we have significant uplift in erosion sometime between 2445 and 2280, which is recorded by a detrital study of zircons from the meteorite bore member. And this is showing that it's sourcing material from the Wangara rhyolite, which is about 1.5 kilometres stratigraphically below it. So there must have been some pretty significant uplift in erosion in the southern Pilbara at that time for that to have happened. So we're thinking that this 2400 actually marks the beginning of the ophthalmic orogeny. So following this main orogenic event, we've got these repeated episodes of intracratonic reworking and fault reactivation, which is remobilizing gold around the place. So at 1770, we've got gold mineralization at Mount Olympus, and this is associated with the final stages of the Capricorn orogeny. And during this time, we're getting a change from dominantly compressional to strike-slip reactivation along the faults. And at 1680, we're getting widespread gold mineralization throughout the whole area and also hydrothermal activity. And this is all associated with reactivation along the major faults during the Mangaroon orogeny. So we can use this information to help us with our exploration targeting. So for exploration targeting, we need to be able to link our crustal scale features to our prospect scale features. And so by doing this, we can go back to the seismic transect. So we've got these major faults. So for having an adequate crustal architecture for gold mineralization, we need to have major faults or their secondary structures that extend through to the mantle. These things tend to be quite steeply dipping. They tend to have long reactivation histories, which were established well before the gold mineralization. And also they tend to have opposing lithospheric blocks, which the Bearing Downs fault does, and it's likely that the Nanjalgardi does too, with newer interpretations. So what we think is happening is we're getting the primary gold mineralization happening at 2400 with the orogenic gold, and then we're getting constant upgrading and movement of gold through the crust during these intracratonic reworkings. So we're getting at Star of the West and Belvedere, we've only got fairly small deposits there, and they've both only got the 1680 gold mineralization event, whereas Mount Olympus and Paulsens are both bigger than 1 million ounces of gold, and they both have at least 3 episodes of hydrothermal activity and gold mineralization. So from this study, what we're thinking is we've got crustal architecture is associated with the orogenies, and then we're getting gold mineralization, hydrothermal fluid flow, and fault reactivation all happening at the same time. Okay. Sorry, next slide. And these are just all my sponsors that I'd like to thank for funding and support throughout my project. Thank you.